What comes next is the following question. How do we relate different geodetic frames? So you remember we made a distinction between system and frame. And I mentioned also that in practice, we make transformation of coordinates between frames. We can define the relationship between systems, but in practice, we do what we have available to us, and those are the coordinates, and which basically materialize the frame. So there are three different ways that such relationship has been established, has been performed. The first one is the similarity transformation that we discussed before. Similarity transformation, Helmert transformation. The second one, another one, is the use of the so-called differential Molodensky expressions. And finally, we can also use multiple regression equations, which is a procedure that has been used a lot by the Department of Defense of the US, and also here in Canada, in South America, in Australia, and other places. So let's have a look at these three different ways. But first of all, I want to present a definition in terms of terminology that I'm going to use here. I'm going to call, well, first of all, I have to admit that I don't like these certain terms that we use, but we use nonetheless. So let's define, to be consistent with the discussion we're going to have here. We're going to call classical geodetic geodetic frames when we refer to the geodetic systems materialized using astronomical and or terrestrial observations. We are going to call a hybrid geodetic frame the ones that refer to geodetic systems materialized using astronomical and terrestrial observations and space-based observations. So we are basically, the hybrid it contains terrestrial observations, may contain astronomical observations, and will contain at least a few points that have been determined using space-based observations. And we have the space-based geodetic frames, which refer to the geodetic systems which are materialized using space-based observations. So that's purely space geodesy. And there is a hierarchy among these three names I'm using: classical, hybrid, and space-based G-frames. And I'm going to use this rule of thumb, which is space-based G-frames are better than hybrid G-frames and are better than classical G-frames. You know, G-frame, G-system, the letter G I'm using to represent geodetic. And just to give an idea in terms of order of magnitude, in terms of relative accuracy, Space-based G-frame would be 10 to minus 9, or 1 part per billion. This would be the relative error, or relative accuracy. Hybrid will be 10 to minus 7, or 10 parts per billion, and classical 10 to minus 6, or 1 part per billion. Now, these numbers I'm giving, they intend to give an idea. They are not absolute numbers. They don't mean that any, say, classical G system has a relative accuracy of 1 part per million. Okay, the best ones will be at that order of magnitude, and we can think that there are others that are less than that. And also the hybrid, I may be actually being very optimistic here, quoting 10 to minus 7. But anyway, so just so that you understand, this is just to give an idea. Okay. One of the methods then is using similarity transformation. We have discussed that already, so I'm not going to talk much about similarity transformation. I'm just rewriting. Oh, let me use the pointer here. I'm sorry. Okay. That is better to follow, I admit. So what we have is, I'm just writing here the expression of the similarity transformation. Okay, I have going from a system G1 to a system G2. And what I have here, the coordinates of a point. We apply 3 translations, 1 scale factor, and we apply 3 rotations, 1 scale factor, and 3 translations. These are the 7 parameter transformation that is now the commonly done to relate space-based geodetic frames. But we can use, and we used to use also similarity transformation to relate among classical G frames. But because the quality of these frames, the relative well, we can say the relative error associated with these frames was much larger, we would apply just the 3 translations. So among G frames, 7 parameter transformation, among classical and space-based, the 3 parameter transformation. That was the usual case. The differential Molodensky expressions. Now we are talking about using 3 translations, okay, 3 translations, delta x, delta y, and delta z. Let me point this here. Delta x, delta y, and delta z. Okay, to compute, and other parameters, I'm going to discuss them, to compute corrections for latitude, longitude, and geodetic height. And we'll then apply these corrections, these are constants, apply to system 1, or to go to system 2. Okay, so these would be then classical, 1 would be classical, and 2 would be space-based system. What are the parameters we need for this computation. Of course, we're going to have the latitude and the longitude of the points. And we have here delta A is the difference between the major semi-axis between of the two systems, of the two reference ellipsoids. Rn represents the radius of a curvature of the prime vertical section. E squared is the first eccentricity. A is the parameter of the classical geodetic frame. B is also, this is the minor semi-axis. A is the major semi-axis. Delta F is the difference in flattening. And R sub m represents the radius of curvature of the meridian section. So this is how it is done. Okay, and what happens is that the Department of Defense, there is an agency inside the Department of Defense that is called the National Geospatial Intelligence Agency, or called NGA. It has a huge list of transformation parameters relating local geodetic datums, that would be our classic G frames, and WGS84. WGS84 is the geodetic system used by GPS. Okay, so what the military wanted, they wanted to essentially be capable of relating coordinates obtained given by GPS with the local coordinates everywhere in the world. And then they were occupying common points, and not that many, because they're basically just estimating 3 parameters, and then they use these differential Molodensky expression. So we can see differential Molodensky expression as a different way to use just 3 translations. And finally, the multiple regression. Multiple regression is a way to also model the distortions of the network. It is used to relate classical geodetic systems with hybrid or space-based. So the idea here is that we are moving from a classical system, which has a relative error of 10 to minus 5, 10 to minus 6, to a hybrid, which is already 1 or 2 orders of magnitude better, or to a space base that are going to be 3 orders of magnitude better. So what happens is that the just computing 7 parameter transformation, we still have a lot of high residuals, okay, which are the distortions of the classical network. They become visible. So the multiple regression will be a way to model these distortions. And how it's done? First of all, we go and compute There should be an animation here. Oh, only works if I take the pointer out. Okay, so the first bullet is compute delta phi and delta lambda between the set of common points. Delta phi and delta lambda will be the difference in latitude and longitude between both frames. And then, so what we have here is basically indicating the location of the points in these blue ellipse, and the arrows would be the value, the amount of delta phi and delta lambda. And we can see that, of course, for each point, depending on the region, depending how the classical network was developed, depending on how the error propagated through the classical network, the magnitude of the difference in latitude and longitude is going to vary. Okay, it's not going to be something uniform. So we then model this field. So we create like a field, a distortion field. We model this field for delta phi, delta lambda by means of a polynomial regression, okay, or multiple regression. So here we have a surface here. And then we're going to, so this surface now, here we have the two expressions. I'm just writing here a quadratic polynomial. It's not a prescription, it's just an example. And obviously what we have here are the coefficients that have been estimated and the arguments tau. So if you want to know, so these represents the surface, okay, for latitude and for longitude. So if you want now to determine coordinates of points, okay, here we have these points. These are points that we don't know the delta phi, we don't know the delta lambda. So we know the coordinates in the classical system. We want to get the coordinates in the space-based system. So we just go and apply the polynomial given the coordinates of the point in the classical system. We can, with the polynomial, with the multiple regression expression, we can determine the values of the correction, because this would be now a correction. This would be representing, well, this would be a transformation value for latitude and longitude, and then it would have the value for the second, in the second system. This way of doing was applied in a few cases. We had these done for the first time, if I'm not mistaken, to establish the relationship between the North American datum 1927 and the North American datum of 1983. So these multiple regression expressions are embedded today in any GIS package, in any package that you can think of that will provide an 827 and 83. They are using this transformation. There is also the same transformation done between the South American datum of 1969 and Sirgas. This is the geocentric reference system adopted in Brazil and in South America. The Australians also did the same to relate their classical network and the new space-based network. So these are the three different ways of relating between geodetic Cartesian coordinate frames.